In this lecture, I'm going to talk about some of the material in Chapter 2 primarily of the book Finite Volume Methods for Hyperbolic Problems on the derivation of conservation laws and how we derive first-order hyperbolic systems of equations, and talk about a couple of other aspects as well as some examples. So the sort of equation that we're going to be looking at primarily is a first-order linear hyperbolic system to begin with, qt plus aqx equals 0, where q is a vector of unknowns or conserved quantities. There might be m of them, so we'd have a system of m equations, in which case in the linear system, A would be an m by m matrix, constant coefficient to begin with. A more general conservation law would have the form qt plus f of qx equals 0, where f is a flux function that maps vectors with m components into fluxes, another vector with m components. And what we'll be looking at primarily here is how we derive such equations from physical principles. This conservation law can also be written in this quasi-linear form if we take f of qx and replace it with f prime of q times dq dx, in which case this f prime of q matrix is the Jacobian matrix. In the linear case, f of q would just be a times q. That's the linear case up here, in which case the Jacobian matrix df dq would just be the matrix A. But more generally, we'll see that we can derive nonlinear systems of conservation laws as well. These systems of differential equations are called hyperbolic if the matrix involved, either the A matrix or the Jacobian matrix f prime of q more generally, is a diagonal matrix, diagonalizable matrix that has real eigenvalues. And that's very important in the theory of hyperbolic equations. The eigenvalues, as we'll see, correspond to wave speeds with which waves propagate, and the eigenvectors tell us something about the relation between the different variables in waves that are propagating at different speeds. So we'll look at that a lot more in more detail later. By the way, you may be familiar with the second order wave equation, ptt equals c squared pxx, which involves second order derivatives. As we'll see later, the acoustics equations can be written in this form, but the more natural form that we're going to derive them in and solve them in the work we do here will be the first order system form of the acoustics equations, which we'll see later. So to derive a system of conservation laws, the basic idea is that the total mass of some quantity is conserved except for the way that it's flowing. And we're going to start out in one space dimension. Later we'll look at how this can be extended to more than one space dimension. But in one space dimension, and to begin with, let's just look at just a scalar quantity, which we'll call q. Q of xt is some scalar that represents in one dimension the density function for some quantity, some conserved quantity that we're interested in. And the fact that it's a density function means that if we integrate this quantity between x1 and x2, if we think of this as modeling flow in a pipe, for example, then the integral from x1 to x2 gives the total mass of that quantity in the interval from x1 to x2. And the idea of the conservation laws that we'd be driving, to start with at least, is that the only way the total mass in this interval changes is by flux through the left boundary or flux through the right boundary. Only if this quantity is flowing in or out of this section of the pipe does the total mass in between change. And so we can use that to drive a conservation law. And again, in one dimension, we're sort of assuming things only vary in the x direction. So if you think of this as a three-dimensional pipe, we're assuming that things are constant in the cross pipe direction and only vary along the length. So if we assume that the total mass can change only due to the flux at the endpoints, then the time derivative of this total mass, so total mass again is the integral, the time derivative of that integral is given by the rate at which material is flowing in at left boundary, some f1 of t, minus the rate at which it's flowing out at the right boundary. So f corresponds to flow to the right, and so we have f1 minus f2. And the basic idea in driving the conservation law is that these fluxes are somehow functions of the value of the conserved quantity itself. and that f of q is what's called the flux function. So if the function q is smooth enough, we can take this equation that the time derivative is the jump in f, and we can do some manipulations to it. We can move the time derivative inside the integral so that we get the integral of dq dt with respect to x. And this difference in the fluxes, it's some function f at q1 minus the same function f at x2. We can write that as the integral of df dx integrated from x1 to x2. And we pick up a minus sign here because it's the f at the left boundary minus the right boundary. And so we have a minus sign there. If we move this over to the other side, though, it becomes a plus sign, and we can write this as just the integral of dq dt plus the f of x, the x derivative of f of q, rather, qt plus fx. The integral of that is equal to 0. So that comes directly from this conservation law, again, assuming q is smooth enough. And now, because this should be true for any x1 and x1 and x2 are just any two arbitrary points along the pipe, and if we have conservation everywhere, then this integral should vanish for all choices of x1 and x2. And so again, assuming things are smooth enough, that implies that the integrand itself must vanish. And so we come up with this differential form of the conservation law, that dq dt plus the x derivative of the flux f of q is equal to 0. And for some cases, this differential equation is the easiest thing to work with, but this integral form of the conservation law that's up here at the top is really the more fundamental form, and for some situations it's much nicer to work with that form than with the differential equation. In particular, hyperbolic equations often have discontinuous solutions. We can have discontinuities that simply propagate in a linear hyperbolic equation, and in a nonlinear equation, even if you start with smooth data, discontinuities can form, shock waves can form and propagate. And so we need to be able to handle discontinuities in the solution. And that's very hard to do from this differential equation because the derivatives are not well defined at the discontinuities, and a big part of understanding what happens with a nonlinear shock wave propagation, for example, is understanding how that shock wave behaves. What speed does it propagate at? How does it evolve with time? And you can't see that directly from the differential equation typically. Whereas this integral form of the conservation law up here at the top, this integral form involves integrating the solution over some finite interval and looking at the flux as a function of time at the edges of the interval. And even if there's a discontinuity in the interval, or if the flux has a discontinuity in time, you can still make sense of this integral form of the conservation law, even for discontinuous problems. And so we'll rely on this very heavily when we start looking at shock waves in particular, but understanding discontinuities more generally. Also, for numerical methods, the finite value methods that we use are based directly on this integral form. If you think of this integral from x1 to x2, if you think of x1 and x2 as being a single grid cell with some grid spacing delta x, and here's our interval from x1 to x2, then this integral of q over that cell, if you divide by delta x, gives you an estimate of the cell average, the average value of q in the cell. And this differential or integral form of the conservation law can be used to evolve the cell average from one time step to the next. And so the finite value methods are based very much on this integral form of the conservation law rather than the differential form. So let's look at an example. The simplest case is what we call the advective flux. If rho is the density, the mass per unit length of any conserved quantity that's simply flowing down a one-dimensional pipe, then if we define that rho with units so that the integral from x1 to x2 of rho gives the total mass in that interval, then from this conservation law, we can write down the corresponding equation for how rho evolves. And let's suppose that u of xt is the velocity at which the flow is moving down this pipe. Again, it's assumed to vary only in the x direction and perhaps with t, but not in the cross pipe direction. In that case, if we look at how much material is flowing past any point in this pipe at a given time, well, it's proportional to the density, how many molecules per unit length there are at this point, but it's also proportional to the velocity. The faster it's flowing, the more molecules per unit time are flowing past this point. And the advective flux is simply the product of those two. And in terms of units, if density is in mass per length and velocity has units of length per time, then this product is in units of mass per time. So it would be, for example, if we had grams per meter and meters per second, then the flux would be in grams per meter passing a fixed point. And so that's the flux function. And so if we put that into the conservation law that we had on the past page, what we have is that the time derivative of rho plus the x derivative of the flux, which is just rho times u, is equal to 0. And so this continuity equation, as it's called, or conservation of mass equation, is really fundamental. And many systems of conservation laws involve a conservation of mass equation that's somehow very similar to this, that if we have some density per unit length, and it's flowing with some velocity u, then conservation of mass tells us that rho t plus rho ux equals 0. Now, rho could represent the density of a gas, a compressible gas that's maybe compressing and expanding in the pipe, but it can also represent the density of some, say, tracer that's simply being carried along in an incompressible flow. So let's look at that case first. Let's suppose we have flow in a pipe, and the flow is moving at a constant velocity, u, and now I'll use q rather than rho. We often use rho for the density of a gas, for example, but let's use q for the density of something that's being carried by this flow that's moving at constant speed. So it's a contaminant or a chemical that's present in very small quantities. And so if q is the concentration per unit length of this tracer, then the advective flux, if it's simply being carried at some constant velocity u, the advective flux would be f of q is u times q. And so if we plug that into our conservation of mass equation that we had from the previous page, we've now got q in place of rho, but we have qt plus uqx equals 0. And if we're given some initial conditions that at time 0 we have some q0 of x as the initial distribution, for example, maybe this function that's drawn down here, then what happens with time is that initial concentration simply gets carried downstream, and it doesn't change at all, it just translates along. And in fact, you can check easily that the true solution of this advection equation with these initial conditions is q of xt is just q of x minus ut at time 0. Differentiate with respect to x or with respect to t and combine them, and you see that the differential equation is satisfied. Okay, so at the moment we're not looking at boundary conditions, we're looking at what's called the Cauchy problem, where we assume we're given the initial condition for all x, and this would be the solution then for all x. Later we'll look at how boundary conditions might come into this. But this is the simplest case of the sort of conservation of mass equation, in this case for the mass of some tracer that's being carried along with flow of incompressible fluid, say, at constant velocity. Now, in compressible gas dynamics, it's a little more complicated because the density rho might represent the density of the gas itself in the pipe, and so that might change as the gas is compressed or as it expands. And in that case, the velocity u would also be a function of x and t. It wouldn't necessarily be constant the way it would have to be in an incompressible fluid going through a pipe. It could be, if there are variations in u, then that could be causing compression and expansion of the gas. And so we have not only the density as a function of x and t, but we also have the velocity as a function of x and t. And the product of those two, rho times u, is the momentum, or it's really the density of momentum, the momentum per unit length, in the same way that rho is a density of the mass. And so the total momentum in some section between x1 and x2 would be the integral of rho times u from x1 to x2. And so we can derive a conservation of momentum equation similar to the way we derive a conservation of mass equation for the momentum. And so for the conservation of mass equation, we have the advective flux that's just rho u for the conservation of mass. But then rho u also represents the momentum, and when we look at the conservation of momentum, we have an advective flux that if we have some momentum distribution along the length of the pipe and it's now flowing, then that momentum moves along at speed u, whatever u is locally. And so there's a momentum flux that's rho u times u. But then there's also another term that I'll talk about in a moment, the pressure that comes into the momentum flux, and we'll see where that comes about in a second. But it turns out that for the momentum, the flux is rho u squared plus p. So we end up with a system of two conservation laws in this case, one for the density, rho, and one for the momentum, rho u. They're both conserved. They have different flux functions, rho u and rho u squared plus p. And so we get a system of two equations. Now, we might also have a conservation of energy equation, and we'll look at more complicated cases where we do. But in the simplest case, we might just have, in some cases, isentropic flow or isothermal flow, for example. You can model the gas dynamics with just these two conservation laws. But we need one more thing, because the pressure here is also a function of x and t. P is the pressure, and these equations by themselves don't tell us how the pressure evolves. And pressure is not a conserved quantity the way mass and momentum are, so we don't derive a conservation law for pressure. Instead, we typically have what's called an equation of state, which for the simple cases that we'll look at first, the equation of state simply says that the pressure can be written as some function of the density. Later, we may see that if we have a conservation of energy equation, the pressure might also depend on the temperature of the gas, for example. But if we're looking at something like isothermal flow, where we're assuming the temperature is constant, then you can model it with this more simple system. So you need the two conservation laws plus this equation of state in order to define the simplest version of compressible gas dynamics. But again, it can be derived in much the same way as we looked at for just the advection equation, and the rho u and the rho u squared terms in the fluxes are exactly advective terms. So we end up with these equations, but it's a little mysterious why the pressure comes into the momentum flux, for example. What does that represent? So let's talk about that for a moment. So there's a couple ways to look at it. One, just looking at the differential equation, you can view the dp dx term that's in the momentum equation here as being a force that's accelerating the fluid. If there's variation in pressure along the length of the pipe, then gas is going to be forced from the high pressure region into the lower pressure region. And so even if it starts with zero velocity everywhere, it's going to accelerate as it moves from high pressure to low pressure. So there's a force that's proportional to the derivative of P with a minus sign, because high pressure to low pressure causes a positive change in momentum. So that's one way to look at the derivation of this, but that doesn't quite fit into the framework we've been looking at with deriving things in terms of fluxes at the boundary. How does that pressure correspond to a flux at x1 and x2 and differencing those? Well, to understand that, we really have to look more at sort of the microscopic motion of gas molecules. When we look at these equations, this u that we're talking about here is really sort of an averaged u, the bulk velocity. If you average over all of the huge number of gas molecules, their average velocity is what we call u, which, for example, if the gas is at rest in this pipe, the average velocity would be 0. But microscopically, the velocity of the gas molecules is not 0. They're bouncing around all over the place. And so if we looked at sort of how these gas molecules are moving around, then we can view the pressure as an indication of how much, hypothetically, if we put a wall, say, in here at some point x1, what would the force on that wall be by the molecules hitting it from one side or the other? And so if the molecules weren't free to pass that point, but instead were bouncing off of it, then they would be applying a force to that vertical line. So you can think of the pressure at any point as sort of being that hypothetical force that would be applied to a wall if you put a wall in at that point. And of course, that pressure is going to increase if the molecules are vibrating in a certain way, but you double the number of molecules, then there are going to be twice as many molecules hitting the wall per unit time, and so the pressure would increase as well. And so this equation of state that says that the pressure increases with density, for example, relates directly to this idea. You can also increase the pressure by increasing the amount that these molecules are vibrating, increasing the temperature, for example, if we look at more complicated situations. But that's the basic idea of the pressure. But how does that relate to a flux past an interface? So now if we think of x1 as being a point that these molecules are simply going back and forth across, then the idea that the pressure is a momentum flux comes from the idea that if you look at the molecules that are crossing this boundary x1, say from left to right, then as a molecule crosses from left to right, it's bringing positive momentum into this interval from x1 to x2. So if we had our other interface x2 over here, then any molecule that's crossing from left to right is bringing positive momentum into the interval x1 to x2, and so it's increasing the momentum in that section of the pipe. On the other hand, the molecule going from right to left across that same boundary is removing negative momentum from this section. And when you remove negative momentum from this section, you're also increasing the remaining momentum in this section. So regardless of whether a molecule goes from left to right or from right to left across this interval, either way it increases the momentum in the interval from x1 to x2. Okay, so even though the sort of net change in momentum might seem like it shouldn't change if you just have this microscopic variation, if you look at a single line x1, the variation, the pressure coming from the oscillations of the molecules is really constantly increasing the momentum between x1 and x2. Of course, the same thing is happening at x2. You have molecules going to the left and to the right across x2, and the ones going to the right are now removing momentum from this interval. The ones going from right to left are bringing negative momentum, so they're also decreasing the momentum between x1 and x2. So the net effect, if the pressure were the same at x1 and x2, the net effect is that the total momentum between x1 and x2 wouldn't change. If the difference in the pressures is zero, there's no change in the momentum. But more generally, if you have different pressures at x1 and x2, then they're changing the momentum in different ways. And so there's a flux in momentum that's proportional to the pressure at each point, and the time derivative of the integral changes by the difference in pressures, exactly the same way that we derived other conservation laws. So that's why the pressure comes in as a momentum flux in the gas dynamics equations. Okay, let's shift gears a little bit. I want to just briefly mention the idea of source terms and balance laws, and we'll look at this in more detail later. But so far I talked about a conservation law where we end up with Qt plus Fx equals 0 because things are conserved within an interval, and that was based on the assumption that the total mass in the interval could only change due to what's flowing in or out at the two boundaries. But now if we look at what's called a source term, psi of q, there are situations where the time derivative of the total mass of something in an interval is not only changing due to the difference in fluxes at the two ends, but also due to some process that's happening over the entire length of the interval. So it's not just happening at x1 and x2, but sort of everywhere in this interval there's some external force or something that's going on that's changing things within the interval. And so that can be represented typically as an integral from x1 to x2 of this source that's happening at each point in the interval. And so when you put these things together, you get and do exactly the same thing we did before of rewriting this as the integral of the f dx, and then combining all these, moving the time derivative inside, you end up with this differential form that has a source term on the right-hand side. So for example, if we looked at the advection of several different chemical species down a pipe and they were reacting with each other, then even though there might be conservation of the total number of atoms of each type, when you look at concentrations of different molecules, they might be changing not only to the fact that they're flowing, but also to the fact that chemical reactions are going on. And so the mass per unit length of one type of molecule is decreasing while the mass per unit length of a different type of molecule is increasing. And those reactions are occurring not just at the boundary of the interval, but also everywhere along the interval from x1 to x2. So you get that sort of source term. Another example is if you have gravity. If we look at compressible gas dynamics in a pipe that's oriented vertically now instead of horizontally, and we have the force of gravity going downwards, then there's an additional force that's acting on the gas everywhere, and you have to put that in as another forcing term in the momentum equation, and that's being applied to all the gas molecules everywhere in the pipe. There are various other types of source terms that we'll see in other applications. So a very simple example would be if we just have advection of a single quantity, but now suppose it's a radioactive isotope that we're looking at the concentration of as it propagates down the pipe. So it's decaying into something else, but let's just look at the mass of this one particular isotope. Then at each point in time, we would expect its time derivative to be just like minus lambda times q, exponential decay. And so that would define our source term as a function of x and t. If we didn't have any advection, we would just have exponential decay of this particular isotope everywhere in the pipe. But if we add this now to advection, so if we just looked at that, we would have that conservation law, but when we add it to the advective flux, if it's also flowing at the same time that it's decaying, then we end up with a conservation law that gives us qt plus uqx equals psi of q as our conservation law in that case. So, although it's not really a conservation law now because this is not being conserved, it's decaying as it moves along, so it's often called a balance law. If we go back here, I think I had that on the previous slide. The term balance law because there's really a balance between the fluxes and the source term often. Another example that's important is to look at a diffusive flux. So this is going back to sort of how do we derive a conservation law. This could be a conserved quantity, but instead of simply advecting, it's also diffusing. So if we have a very small concentration of some chemical in water that's moving down in a pipe, then even if there's no advective flow, even if it's stationary, if you have a very steep gradient in the concentration, then due to molecular diffusion, as these molecules are randomly vibrating, you expect them to spread out. And that sort of diffusive flux is typically proportional to the gradient of the concentration, or to the x derivative of the concentration in the one-dimensional case. So beta here is some positive coefficient, and the flux is proportional to minus beta times dq dx. So if the concentration is increasing, if q of x is positive, then there's a flux from right to left. It tends to diffuse from the more concentrated region to the less concentrated region. So the flux now depends on dq dx, and so when we put that into our conservation law, qt plus fx equals 0, we end up with qt equals beta times qx, the x derivative of that, since beta qx is our flux. So we end up with this diffusion equation, or you also, in the case of heat, you have a very similar sort of equation where you end up with time derivative of q is some coefficient, some positive coefficient, times the second derivative of q. And this is a parabolic equation rather than a hyperbolic equation. So it has different characteristics than the sort of wave propagation equations that we'll primarily be looking at, but it's important to understand that you can also have, in many hyperbolic systems, there's also some diffusive or viscous terms that come in that often add in these parabolic terms, which can in some ways complicate the solution process, as we'll see, but also can help us with the mathematical analysis sometimes. So a simple example would be the advection diffusion equation, where we have a flux that's not only the advective flux u times q if we assume flow at some constant speed u, but also some diffusive flux minus beta times dq dx, and then we end up with this advection diffusion equation. And again, it's a parabolic equation, but in many cases, we may have a situation like this where u is much larger than beta, and this ratio u over beta is called the Peclet number often. And if that's very large, then the advection is dominating the diffusion, and in such cases, sometimes you can approximate it by just a purely advective wave equation, advection equation. Similarly, in fluid dynamics, there's always things like thermal diffusion. Heat is diffusing if you have temperature gradients in your flow. Also, momentum diffuses in the form of viscosity. If you have viscous terms in the equation, then you also get second-order derivative terms, diffusive terms that are similar to what comes into the advection diffusion equation. And in the real world, fluids typically are viscous and do have thermal diffusion going on. So a more proper model of fluid dynamics, Navier-Stokes equations, typically include these parabolic terms. But we're often interested in situations where those terms are relatively small compared to the hyperbolic terms, and so you can ignore the second-order derivative terms and reduce things to just a first-order system of conservation laws, which can make things simpler. On the other hand, as I mentioned, first-order systems of conservation laws can have discontinuous solutions, shock waves, whereas parabolic equations don't. Parabolic terms tend to smooth things out, and so you have nice, infinitely differentiable solutions for all time. And so when we try to analyze shock waves and understand better what the right speed for a shock propagating is, for example, it becomes important to look at the viscous equation and remember that the equation we're solving is really the limit as the viscosity goes to zero, or as some other diffusive term goes to zero, of a parabolic equation that has a well-defined unique solution. So in the case of just the advection diffusion equation, for example, if we just had the advection equation, we could have a discontinuity that simply advects. Remember, any initial data simply shifts with constant speed u. So if we had a discontinuity like this red curve here, it could just be shifting along with speed u and remain a discontinuity. If you instead look at the advection diffusion equation, though, it would smear out immediately and become a C infinity function for all time. So the real way to understand the discontinuity in the solution of the hyperbolic equation is to remember that it's really the solution typically of a viscous equation, but the viscous parameter is so small that we'd like to ignore it. So we can look at what happens in the limit as this parameter epsilon goes to zero. So as we decrease epsilon, the solution of the parabolic equation becomes more and more like this discontinuous solution of the hyperbolic equation. So this approach is what is often called the vanishing viscosity solution for fluid dynamics, and we'll use this when we look at shock waves down the road. Okay, well, that was a quick overview of the way that hyperbolic conservation laws and some other conservation laws are derived, and also source terms in the case where we have balance laws.